Yesterday I spoke about sort of learning spaces mostly, and how we can break down the walls of the classroom. Today is very different. I'm going to reflect back on my my trajectory as an instructor at Harvard. You see, when I started teaching at Harvard, we didn't have a Center for Teaching and Learning. In fact, no universities had centers for teaching and learning 30 years ago. It's something that's relatively new. We didn't get any training in teaching. We were just asked to teach. And as a young assistant professor, I was asked to teach the course that nobody wanted to teach: physics for pre-medical students. These were not students who wanted to learn physics. No, they already hated physics before coming into the classroom. But in order to get into medical school, they had to take physics. And same for engineering students. You know, they were really looking forward to their physics course. And you know, since pre-medical students and engineering students don't like physics, they tend to lower ratings at the end of the semester, and therefore my colleagues do. I didn't know any of this, so plus I just said whatever they asked me to teach. And since I got training, how did I teach? I essentially teach by lecture. Here's a picture of me. This is a very old picture. It was taken BC, before computers. And then something interesting happened over the course of the first few years that I was teaching. Students liked how my lectures, and they gave me high ratings. So I very quickly got feedback that I was actually doing a good job. You see, it's actually interesting, right? When you start doing something new in your life, like I was at the time of that picture there, the first question you should ask yourself is, how am I going to teach? That question did not come up in my mind. It's completely obvious what I was going to do in a classroom. I was going to do to my students what my professors had done to me, lecture. I think we all tend to do that. We tend to project our own experiences on the world around us. We see, you know, our lives through the lens of our previous experiences. And I naively thought that I had learned physics by listening to my professor's lecture, like I did here. Now, I started lecturing, and at the end of the first year, I got very high ratings. You know, 4.8 for my lectures, 4.8 on a 5-point scale. Clearly, my students liked the way I was learning. And I could give them some very hard problems on exams, problems that I wasn't sure I would do well under the pressure of time and an exam. So they liked me as an instructor. They did well on what I considered a difficult exam. Obviously, I was doing the right thing. In fact, given that my colleagues were not very successful at teaching this course, I very quickly started to believe that is there a sound problem?
Yeah, we're putting it a bit higher.
Okay, good. I hope that the people in the remote setting can hear me.
Just a minute.
Do you want to set it on in the
It's
settings?
brio?
Okay, good. Stay a bit closer. I can stay a bit closer, but then I know the view of the camera.
Yes, but I'll follow you. I'll follow you with my camera stand.
Okay, good. So, you know, given that positive feedback, I was very quickly, you know, led to believe that I was the world's best physics teacher. After all, my colleagues were not successful, and I was not. Now, this approach to teaching, that turned out, by the way, that turned out to be a complete illusion. I'll get back to that in just a second. Now, this scene that you see here, I showed that yesterday, but I don't think many of you were there yesterday, is incredibly close to this picture here from an illuminated manuscript, which represents Heinrich, King of Germany, Emperor of the Holy Roman Empire, giving a guest lecture at the University of Bologna in 1230. I mean, look at it, right in the front row, you see the people paying close attention. They look a little bit less interested in the second row. There at the back, you can see people who look rather bored. And in the back corner on the far right, you can see that they talk to each other, not listening to His Majesty, King of Germany. And you know, and then there's this guy here in front. I don't know if he's fast asleep or cringing, but you have to admit, you see at once that it's a very similar scene, and that very little has actually evolved in education in over 1,000 years. We no longer wear these robes. Well, actually, we still wear them in graduation and ceremonies to remind ourselves that we are steeped in medieval traditions. But other than clothing, it looks very, very similar in terms of space and setup to this very classroom where I'm right now. So let's go back for a moment to this picture of me around 1990, so 30 years ago. I would like you to describe to me in 1 or 2 words the process that is taking place on the screen behind me. And ideally, I want one of those 2 words to be a verb. But there are 2 verbs I do not want to hear: teaching and learning. So you have to find other verbs. So go ahead. It's not a trick question, don't worry. Just blurt it out.
Communicating.
Communicating.
Education.
Education.
Engage.
I missed it.
Engage. Engage.
Okay. So by the way, communication, I consider communication a 2-way thing. Right? Me to you, you back to me.
Interaction.
Interaction, same thing. You know, does this look very interactive to you?
Yeah.
No. In fact, it's very difficult to interact with you right now here. Why? Because this space is set up like a theater. When you came in here, you were thinking, I'm going to listen to Eric Mazur lecturing. And I'm sort of breaking that by asking a question and trying to interact. But you know, you bring the same mindset to a classroom that is set up like this as you do when you go to a theater or a movie. So it's not interaction. It's not communication. What is it then?
Like a streaming of knowledge.
A streaming of knowledge. Reminds me of a cartoon I saw from a French artist, where you see a classroom and there's a machine with wires connecting to the brains of all of the students, delivering the knowledge to the brains. But is knowledge something you can transfer?
No, exactly. Communication, according to Ghent models, assume that our communication receiver is a co-creator of communication knowledge. You get to refer to the prior knowledge, to the experience, to the fears and problems. And we can address that. We can solve the knowledge as an study process.
Okay, that's a very, I said 2 words, remember?
I wanted to explain communication.
But I don't think it's communication. I'm much more inclined to accept transfer. I just have a problem with the word knowledge, because I don't think you can transfer knowledge. It would be great if you could transfer knowledge. It would be even better if you could transfer knowledge while people are sleeping, which most of them are actually doing.
Yeah, but
So-
isn't it the idea of the lecture behind the transfer of knowledge? That you present your knowledge as sharing.
I can present my knowledge, definitely, but that doesn't mean it's being transferred.
I mean, knowledge is something that needs to be constructed in the brain of the learner. You need to construct knowledge in your own mind. And we'll talk about that in just a second. So if it's not knowledge that you can transfer, what can you transfer? Information, exactly, that's what I wanted. Lectures focus on the transfer of information. And you know what? My students had actually pointed that out to me the very first year that I taught. And I had ignored it. In fact, not only had I ignored it, I was upset. You see, I told you a minute ago that when I started teaching, I did not ask myself, how am I going to teach? But I did ask myself questions. Not how am I going to teach, but put yourself in my feet, teaching a course for the first time. What? Exactly, what am I going to teach? So I went to a colleague who had taught the course before, and I asked him that question, and he said, oh, in this course, I have used a book by Holiday Resnick. It's a classic book in physics that has been used for close to 50 years, believe it or not. And he also told me, which came a little bit as a surprise to me, that the students would buy the textbook, and that I had to make sure that the bookstore, the university bookstore, had enough copies of the book in stock. I was educated here in Europe. I don't know how it is in Belgium right now, but in the Netherlands, where I was educated, you can buy textbooks. Why buy the book if the professor is presenting the book to you? Now you can save the money when you're taking notes. Anyway, I did as I was told. I went to the Harvard Coop, which is our bookstore, and I told the person in charge of ordering books, so be sure that by September 15th, you have 150 copies of Holiday and Resnick in stock. And as I walked back to my office, I also started to think, if they have the book, and I have the book, what am I going to do in the classroom? So I went back to my colleague and I knocked on his door and I asked him that question. He said, oh, Eric, don't worry. There are lots of different physics textbooks. And he showed me a shelf full of books that he had collected over the course of his career. And I started to look, and I very quickly found the perfect book. It was a different book from Holiday and Resnick. And the best part was it was out of print. So the students couldn't get a copy of the book anymore. So I used that book, for every lecture, I would work 10 hours and make a set of notes from that book. And then in the classroom, I would either write it on the board behind me or I would project this. Remember, this was PC, okay? So there were no projectors like this. I put it on the overhead projector on slides. By the end of the term, what happened? Oh, no, I should say one more thing. So because my notes were different from the textbook, I thought it would be good for my students to get a copy of my notes. So at the end of each class, before they walked out, there were doors in the back, much like here, I would have a stack of photocopied notes. Again, you couldn't post them on the internet because there was no internet. Now, why do you think did I give my notes to the students at the end of class and not the beginning of class? So they would pay attention. But isn't that already admitting that there's a problem? I mean, why force the students to get the information out of my mouth if they can read it from my notes? That question never came up in my mind. But you know what happened? At the end of that very first semester, on the evaluation, about half a dozen students wrote, Professor Mazur is lecturing straight from his lecture notes. Hello? I mean, what was I supposed to do? Develop another set of lecture notes to lecture from that was different from the lecture notes I gave to them? These ungrateful students. I was upset. But they had a point. I was lecturing from my lecture notes. I once heard somebody describe the lecture as a process whereby the lecture notes of the instructors get transferred to the notebooks of the students without passing through the brains of either. That's a joke, by the way. You're supposed to laugh. Well, actually, it's a very sad joke, but it has a lot of truths. You know, people are just registering information, but there where it really needs to get, it didn't get. Well, anyway, I ignored that because I didn't understand it. I didn't understand it. And for many, many years, I continued to lecture, get my high ratings. And you know, the thing is, if you get high ratings, you're asked to teach the course again. And the cycle continued, the cycle and the medieval tradition, because that's what it really is, continued. Now, as I mentioned a moment ago, this idea of being a good teacher that I had in my mind was a complete illusion. It was a house of cards, which crumbled after I taught for about 6 years. Because in the 6 years I was teaching, I read an article in a research journal that claimed that students learn next to zero, next to nothing in an introductory physics course. And the person who published that article published a questionnaire that had 30 questions, pardon me, that essentially test students' basic understanding of the most fundamental concept in physics, force. But rather than testing it using the usual type of problems that we use in the course, it tested it with just words. Let me give you an example. And this turns out to be one of the hardest problems on this questionnaire. A heavy truck and a light car collide head-on on the highway. Boom. Is the force exerted by the heavy truck on the light car larger than the force exerted by the light car and the heavy truck? No. Or are the two forces the same? Or is the light car exerting a larger force on the heavy truck than the other way around? Now, all the students in an introductory physics course can recite Newton's third law. You may have heard of it. It's also called action is reaction, or the force of object from exerted by object 1 on object 2 is equal in magnitude to the force exerted by object 2 on object 1. In equation form, it would be F12 is equal to F21. All the students know that. But apparently, according to this article, if you replace 1 by heavy truck and 2 by light car, the students forget all about, you know, Newtonian mechanics, and they're convinced that the heavier object exerts a larger force on the lighter one than the other way. I saw this and I thought, no way, not my students, not Harvard students. But you know, I'm a scientist, so one of the things you learn as a scientist is not to make any assertions, but to look for evidence. So I decided to give that questionnaire to my students. It took less than 5 minutes for me to tumble out of my ivory tower and for my world to change forever. Because within 5 minutes, one student raised her hand. I went over to her and she looked me right in the eyes and she asked me, Professor Mazur, how should I answer these questions? According to what you taught us, or according to the way I usually think about these things? I went, what? Shouldn't that be the same thing? Shouldn't the way you think about the world be the same thing as physics? Anyway, I didn't even know how to reply to that question. And it was only once the test had been completed and we analyzed the data that I noticed that there was a very big problem. Yes, the students liked my lecture. And yes, they could solve standard textbook problems. but they had not really internalized any of the fundamental principles of physics. You would think it's different here. Well, I've given a test here in Belgium and at the University of Leuven, and it was no better at all. It was the same. So this is pretty universal. I've done it in Taiwan. I've done it in lots of different parts around the world. It's not different. I haven't done it at Ghent, no. But I think I can extrapolate from all the results I have. So that was a rather eye-opening experience, right? All of a sudden, this illusion of being a good teacher was shattered, because clearly I had just trained students how to solve problems without understanding the underlying concept. There was no transfer of knowledge. And if you can't transfer your knowledge, there's no learning. You just are like a parrot, repeating back what you've learned, regurgitating back the information that you've learned. So that was a turning point in my career, and I was wondering for a while, how can it be? Maybe I have dumb students, but that could obviously not be true. Right? I'm at Harvard, and we have a very select admissions. We only take the top 1.5% of students from around the world. So, obviously they could not be dumb. Another possibility was that I was just a bad teacher. And that could not be true either. Right? So I thought about it for a while, and I came up with the perfect excuse. The test had to be bad. So there had to be something wrong with the test. After all, my students were able to solve textbook problems. So I started to do some testing of my own. And on exams, what I did is I put a textbook problem, and next to it, or underneath it, or above it, I put another problem on the same concept, but with just words. And what did I find? I found that students were able to solve the textbook problem simply by classifying it as a specific type of problem, applying a memorized recipe to solve it. But then the word-based problem, which in the eyes of most physicists was totally trivial and obvious, they would fail to answer. So that's when it became clear that the problem that I had was really me not being a very effective teacher. So what did I end up doing? Well, first of all, I asked myself, that's the moment that I realized that I was not transferring knowledge. I was simply transferring information. I was reading the textbook to my students. Where does the word lecture come from? What does lecture mean? I'm giving you a lecture here right now. What does lecture mean? Reading. It comes from the Latin, exactly, reading. It's a reading. In fact, in the UK, you have an academic title, Logan, a professor called reader. It's ironic, right? We use the word to read to transfer information. So I was just transferring information, but the information was not getting where it needed to get in the brains of my students. So I started to think of education as a two-step process. One, information transfer. No information transfer, no education. I think we all agree on that. But that is not enough. That is not enough. The learner needs to make sense of that information, assimilate the information, connect it to pre-existing mental models, extract from the information the knowledge that permits you to apply what you've learned in a situation you have not seen before. Now, to those of you who are no longer students in the audience, ask yourself, where did that happen? Where did those aha moments, oh, yeah, now I get it. Where did that happen? Did that happen while you were sitting in a classroom like this, listening to your professors? I see several people shake their head. No, probably not. It probably happened outside the classroom when you went back home, went over your notes and said, how does this work? I don't figure it out. And then, maybe you talk to somebody, maybe you figured it out on your own, and finally you went, aha. So you might say, well, it worked for us. Obviously, it worked for me, otherwise I would not have become a physics professor. But see, that's the point. I became a physics professor. Most of my students are not going to be physics professors. They don't have the same interest and the same intrinsic motivation to understand things, to figure out things that they couldn't understand in class outside of the class. So for most of my students, they never got beyond step 1. They got stuck at step 1. And then they simply memorized to pass the exam. And then forgot. I heard a term last year during the pandemic from some students in my class describing their other science classes. And they called it cram and flush. Cram, meaning, studying to put as much information as possible in your head. You go and take the exam and then you flush. Clear out the brain so you can cram new stuff in it. Does that ring a bell to most of you are students here?
Yeah.
It's sad, isn't it? It's very, very sad. Because that's not the purpose of education. It's like making you jump through hoops like a monkey for no good purpose. You might think, well, you're going to know a few things. You'll remember the things you need to know by virtue of doing activities in that field, not by having somebody tell you you need to memorize that. Anyway, if you ask yourself, which of these 2 steps is the hard one? Which one would you choose? 2, right? 2 is the hard part, not 1. And here I was, as an instructor in my class, putting all of my emphasis on step 1 and leaving step 2 to my students. If you stop to think about it, we should really be focusing on that second step. That's the hard part. Why is it not forwarding? Here we go. Oh yeah, so in the traditional approach to teaching, this happens in class and that happens outside of class. But we should really be focusing on this as instructors. That's where the students need me the most, because I can help them. So this is what I decided. This gave rise to what is now generally known as the flipped classroom model. I decided to invert that sequence. Let's give students the responsibility out of class for the information transfer. After all, we live in an information age. We've had 2 major information revolutions. The first one was when?
Print and literacy.
It was actually 200 years after that King Henry of Germany gave his guest lecture. It was in 1425 when Gutenberg invented the printing press. All of a sudden responsible to disseminate information, not orally, but printing. And then, at the end of the last century, in the 1990s, we had the internet, which completely opened up the information. Information is everywhere. There's no need anymore for us to read the textbooks to our students and to lecture. So the students are responsible for the information transfer. And then in class, I work on helping the students assimilate the information. And I do this through an approach that I call peer instruction. For some reason, my clicker is not working very well. So I'm going to focus the rest of my talk on the second step. The first step is important too, but I'm going to focus on the second step. If I ask my students to read the lecture notes of the book before coming to class, and in 1990 that was the only thing I could do. Now I could even have them watch or pre-record the lecture on their own when it's best for them. What do I do in the class? Well, the answer to that question is, teach by questioning. Who was, by the way, the first person to say that? It was not me. Who was the first person who said we should teach by questioning rather than by telling? Socrates, exactly, 2,000 years ago. And in the Far East, you had Confucius who said something pretty similar. So for thousands of years, we've already known that we should not teach by telling, but teach by questions. Now, it was not that I was sitting in my office and thinking, what am I going to do? What am I going to do? Oh, Socrates. Oh, I didn't think of Socrates at all. It was a completely serendipitous discovery. You see, after taking that test, the forced concept inventory that I told you about a moment ago, that made me discover that my students didn't learn, I was shocked. But my students were shocked too. I gave it to them 2 weeks before the final exam. And they couldn't believe how low the scores were that they were getting. So they panicked. And they asked me for a special session to explain every of the 30 questions on that test. So I booked a large auditorium. I had 250 students. And from 7 p.m. at night to 10 p.m. And I went through every single question. And I remember coming to the question of the heavy truck and the light car. And I thought, that's simple, it's just Newton's third law. What is there even to explain about it? So I turned around, I made a drawing of the car, I drew the force of gravity, the force of the road up on the car, and then the force of the truck on the car, and then I drew a diagram of the truck, force of gravity on the truck, the force of the road up on the car, and the force of the car on the truck. And then I turned around and I said, by Newton's third law, the force of the car on the truck is the same as the truck on the car. You know, what more is there to explain about it? And I could see from the faces of my students that something didn't click. So I said, is there a question? They were so confused, they could not even ask me a question. You know how it is, right? I mean, if you're really confused, it's hard to express your confusion. So I thought, this is a problem. Yeah, maybe they're confused by the fact that, you know, the forces are the same, but the effects are very different. The effect on the car is bigger than the effect on the truck. But that's because the car is lighter. So I should bring in, you know, Newton's, not just Newton's third law, but Newton's second law. So I raised the board and, you know, I started all over and I wrote the equations and I worked out it. In the next 8 minutes, I gave the most brilliant explanation you can possibly imagine. And after 8 minutes, the whole board was covered with drawings and equations. Of course, I've done it always like my back to them. And then I turned around. They looked even more confused. And they could still not articulate the question. Well, I got some questions, but I didn't even understand what the questions were. So I didn't know what to do. And I realized this was really important. I mean, we had done forces in the first week of the semester. Everything else builds on top of the concept of force. You don't understand force, you understand nothing. So I didn't know what to do. I spent 10 minutes explaining it to them. I didn't know how to explain it any better. So, but I knew one thing. I knew that half of them had given the right answer. So I said, why don't you discuss it with each other? And something absolutely amazing happened. Complete chaos. Okay, all 250 students started talking to each other. It got very noisy. And they completely forgot about me in front of the classroom. I could have walked away, they would not have noticed it. They were all talking about that question. And what was even more surprising was that in just 2 minutes, they figured it out. I thought, how can that be? I, the expert, have tried for 10 minutes in 2 different ways, unsuccessfully, to explain it. And in just 2 minutes, they get it? How is that possible? But imagine you have 2 students sitting next to each other, Mary and John. Mary has the right answer because she understands it. John does not have the right answer, does not really understand everything. On average, Mary is more likely to convince John than the other way around, simply by the force of logic. But that's not the important point. Mary is more likely to convince John than Professor Mazur in front of the class. Why? Because she has only recently learned it. She still knows what the difficulties are that a beginning learner has. Whereas Professor Mazur has known it such a long time ago, he cannot even remember what the conceptual difficulties are. It's what Susan Ambrose, in her book, How Learning Works, I don't know if you know that book, it's a great book, calls the expert blind spot. As experts, we're no longer aware of the mental blocks. And once you understand something, it all becomes clear. It becomes so clear that you cannot understand how somebody cannot understand it. When I saw that, I was like, wow, this is how I need to teach. So the next semester, I decided no longer to lecture. I love lecturing, but no more lectures. And I would tell my students, read the chapter before coming to the classroom. And then in the classroom, I would start asking questions. And then after I put the question on the screen, I give them a minute or two or whatever is needed to think about it. So it's silent, almost like an exam, except that it is not an exam. And after they think about it, I have them vote on the question. Initially, we did this by show of hands, but that turns out not to be that good. So what I did afterwards was putting the hands on the chest. So I used the multiple choice question. Just answer 1, you put 1 finger. Just answer 2, you put 2 fingers. Answer 3 fingers. 4, 5, no more than 5. Okay. You need to know that because I'm going to ask you to. So everybody would be putting their hand at the same time on the chest, and I can see the vote. I try to aim the question so that about half the students, somewhere between 30% and 70%, get the right answer. And then I tell my students, find a neighbor who has a different answer. And try to convince that person that you are right and he or she is wrong. A lot of students talking to each other. A lot of aha moments. You'll see students actually go listen and then go, oh, it's like a light bulb going off. It's just absolutely phenomenal. Of course, you have some students who are sitting in the back row who are not participating. But what I do is I immediately go to the back row and I talk to them, which they like a lot. So the next lecture, they are sitting, more towards the front rather than in the back. That holds for you in the back there too. And then I pull them again. And if you start with somewhere between 30 and 70% correct, it's not unusual to have an overwhelming majority have the, I think I scared one person there. It's not unusual to have an overwhelming majority of correct answers in the second, and many aha moments in between. I wrap up with an explanation, which could either come from me or it could come from one of the students, which is often much better than from me. And then that cycle repeats until class time is up. So very different from what I've been doing right now, but we'll try it out in just a second. And of course, the learning takes place during that discussion. A very different activity from just listening to your professor. You want to try it? You're not very enthusiastic.
Yes.
Okay. Do you want to try it? Ah, good. Okay, very good. So I'm going to give you, since you didn't read before coming to my lecture here, I'm going to give you a very brief 5-minute lecture about your favorite subject, thermal expansion. And then I'm going to ask you a question, okay? So thermal expansion deals with the fact that hard solids, like wood or metal, or concrete, expand when they get hotter and they contract again when they get cold. So if you take a pen and you put it on the stove and you turn on the gas, or if it's an electrical stove, electricity, You know, it'll heat up and it'll expand. It won't get twice as big, won't work. I mean, it'll get a tiny little bit bigger. And then when it gets colder, it shrinks to that. And that's very important in daily life. Engineers have to take that into account. It's actually, it affects everybody and all of us. If you've ever been in a train, and I'm sure you have, at low speed, you hear the clickety-clack sounds of the wheels as they go from one section of the rail to the other, because when the rails are put down, they leave a little gap in between the rails so that the metal can expand in that gap if weather gets hot. If that is not properly done, bad things happen, as you can see from this picture in the background. It goes over hundreds of kilometers, you know, and that expansion becomes very noticeable. Likewise, when you park your car in a concrete parking structure, next time, look down as you walk away from your car. And about every 10 meters or so, you'll see a rubber strip. The building consists of big chunks of concrete, prefabricated concrete often, that are laid down with a gap in between to accommodate this expansion. And that gap is filled with rubber. You may think, well, only engineers need to know this. I don't need to know this. Well, I mean, it affects you too. Next time that you're at your dentist, think about this. Imagine the dentist filling a cavity and putting in the cavity an ordinary metal. If the dentist were to do that, and you were to drink a cup of coffee, that metal would expand more than your tooth does, and you'd be in bad trouble because your tooth would crack, which is why you have to use an amalgam of different metals so that the expansion matches that of the tooth. So it affects all of us in different ways. Now, why is it that solids expand? And I'm only talking about hard solids, right? I'm not talking about soft solids like tissue or gum or bread or anything like that. Hard solids. The reason is that hard solids are made from atoms. I'm showing 9 of them here. And atoms tend to move away from each other when it gets hotter. So this is cold. And this is hot. Cold and hot. That's all you need to know to answer my question. And cold and hot. And hotter, they would move even further away. And hotter yet, they would even further away. And then when you cool it down, they come back. Now, you may wonder, why is it that they get away from each other? Well, the reason is that atoms don't sit still. They shake. They vibrate. And the amount by which they vibrate is related to what we call temperature. So these are cold atoms, and these are hot atoms. Cold atoms, hot atoms. So if you were an atom, you wouldn't just sit like this, you'd be shaking like that. And as it gets hotter, you shake more, and you need more space. You're pushing the people around you away because you need more space to wiggle back and forth. So cold and hot. And by the way, it's not just those 9 atoms, it's all the atoms, the millions and billions of atoms that make up a solid. Questions, anyone? I knew I was a really good lecturer. So thank you for reaffirming that. But you know, I'm not just going to hide this and then ask you, when solids get hotter, do atoms get closer together, same distance, further apart? Because that would be me transferring information to you and you transferring that same information back to me. I'm going to see if you can take this picture of atoms getting further away from each other when it gets hotter, all of them, and apply that to a different context. So you better ask me questions before I ask you a question. Cold and hot. No questions? I'm going to give you 10 more seconds to ask me a question to stop me. There are no stupid questions, but there are only stupid answers when I'm getting the answer. Cold and hot. Are you all ready for my question then? Yeah, you have a question. Go ahead.
He says I have, yes.
So maybe he can ask your question.
The question is, the middle one is not moving.
Ah, very good question. You see, the middle one is not moving. I'm going to tell you why the middle one is not moving. I'm afraid you're not going to like my answer. Here's why the middle one is not moving. I used a program called Adobe Illustrator to make this drawing. At first, I made this drawing in Adobe Illustrator, 9 atoms. And then I made the second one, with the black atoms there, which I made also in Adobe Illustrator. And then I put one picture on top of the other picture. And I put the center atom on top of the underlying center atom. That's why the simple atom is not moving. It's true. You're laughing. It's true. I'm giving an honest answer. But actually, it's a very good question. Because that was a choice, right? I made a choice. Center atom on top of center atom. What would have happened if I would have taken this atom and put it on top of this one? What would have happened to the center atom then? If I would have put this black atom here, then this atom would have gone.
Would start moving.
It would have, in which direction?
Away from
The bottom and the right, exactly. And this atom, instead of moving up, it would have moved towards the right. And this one, instead of moving to the left, would have moved down. And this one, instead of moving this way, would have moved twice as far that way. What matters is not the absolute position of each atom. It's, in most cases, whether I put the top left atom or the middle atom on top of each other, all the atoms would have been further away from each other. And remember, in a real material, there are not 9 atoms. There are not 9 million atoms. There are not 9 billion atoms. There are not 9 billion atoms. No, there are billions of billions of billions of atoms. So the position of any individual atom doesn't matter. Anyway, long answer, but really good question. I think you're ready for my question. Okay, so this is what we're going to do. I'm going to ask you the question, and then when you sit down to think, and then when you're ready, I will ask you to vote. Don't vote before that. And you vote by putting your hand on your chest. There'll be 3 choices, 1, 2, or 3. Everybody at the same time, okay? If you do not put your hand on your chest showing 1, 2, or 3, I'm going to come to you. I'm going to put this microphone right in your face, and I'm going to ask you to tell the entire classroom what your choice is. I do this with my students too. Then I'm going to ask you to find a neighbor who has a different answer. So if you turn to your left, and the person on your left has the same answer, you say, thank you very much, and you turn to the person to your right. If that person also has the same answer, do not talk to that person. You know, talk to the person behind you or in front of you. If everybody around you has the same answer, climb over the seats, find somebody in the room who has a different answer, and trust me, there'll be lots of choices there, okay? Instructions clear? Yes. Good. Okay, so here we go. No more talking until I tell you to talk. So I remember it's all of the atoms. So consider a rectangular metal plate with a circular hole in it. Now we take this plate and we put it in the oven. And we turn up the temperature. And the plate, the metal in the plate expands. What happens to the, what is this? Untitled poll. We don't, oh, this is for
we
people.
are,
Okay.
the audience,
We need to hide it from, we need to hide it from the audience. When the plate is uniform, wow, people knew my vote choice 1, 2, and 3. Very good. Does it increase? Does it stay the same? Or does it decrease? Let's not poll yet, okay, until I ask the poll here. So I think about it. What happens to the diameter of that hole?
What about the force?
No talking, I said. I thought you understood the instructions. For some reason, the wall shows, oh, that's weird. Okay. That's okay.
They can't see it.
Okay, are you ready for vote? If you need more time to think, give me a little sign. I want to think a little bit more. That's perfectly fine. Because I do want everybody to vote. So if you need more time, that's fine. Just let me know. Just wave at me like this discreetly. Does anybody need more time? Everybody's made a choice? Okay, at the count of 3. 1, 2, and 3. I'm not going to put anything. Keep it there. Just, okay, good. So, good. I see 1s, I see 2s, I see 3s, and on the screen I see 3s, 1s, and 2s. Okay, this is not, oh, okay. At least there are no 4s, so that's good. Okay, so find somebody who's a different answer. You've got 2 minutes to try to convince that person.
In your private chats, you don't use
So look at that. You all got fired up. You see the difficulty I had to engage in before. It's not easy, let me tell you. I've been asking you questions, been making jokes, nobody laughed, nobody replied to my questions, and now you are all talking. I am sure that by now most of you have forgotten that I'm not here to talk about further expansion. I am here to talk about pedagogy. And in fact, you've already made my point. The answer to this question doesn't really matter. I've shown you the difference between the engagement in this mode and the lack of engagement before. Isn't it amazing how you can reawaken the curiosity of the human mind? I mean, imagine that I had given my little lecture like I did before, and instead of asking you the question, I would have said, let's now apply this to rectangular metal plates with circular holes in it. If you take one of these plates and put it in the oven and turn up the temperature, the metal in the plate expands and the diameter of the circular hole will, I'm going to keep you in suspense a little bit longer. You would have been sleeping through it. You would have been sleeping through it. What is more boring then rectangular metal plates with circular holes in it. And look at you now. And trust me, you can do this with anything. If you can do it with rectangular metal plates with circular holes in it, you can do it with any subject, okay? Yeah, it's really amazing how you can wake it up to curiosity of the human mind. And you know, if you think about it, small children, you, I, everybody is born a scientist, born a native with an innate curiosity about the world we live in. What do small children do? They never stop asking you why. They want to know the reasons. Why? If anything, education does a really good job killing that innate curiosity of the human mind. And by the time students get to high school and then later college, it's no longer about the why. It's about tell me what I need to know to pass the test. And it's only later in life that we rediscover the beauty of learning. Because we learn for intrinsic reasons rather than extrinsic reasons. Now, you probably want to know the answer to this question. You know, it's totally irrelevant. But let's, before I do that, analyze what happened here. I asked you a question, and then you had time to think about it, and I had you make a commitment. Okay, you had to commit 1, 2, or 3. And once you had made that commitment, I asked you to turn to your neighbor and you had to externalize your answer. I got, what did you get? But it didn't stop there. After that, you moved from the answer or the fact to the reasoning behind it. It was not about it gets bigger, it gets smaller. So many of you gesticulate and try to apply a mental model to the situation. It was not just about, does it get bigger or does it get smaller? Why would it get bigger? Why would it get smaller? Why would it stay the same? And what perhaps most important is that you became emotionally invested in the learning process by the act of committing, discussing, and recommitting. If I were to tell you now, bye, I gotta go, I have another commitment, see you, you'd come running after me, asking me what the answer to the question is. You will not let me leave this room without telling me what the answer is. But I can't tell you the answer yet. Because remember, we're not through the whole cycle. Think, poll, discuss, repoll. So we need to repoll. So at the count of 3, I want you to again put your hand on your chest, and I want you to indicate what you now believe to be the right answer. So if you've not changed your mind, you put the same answer. If you have changed your mind, you put what you now believe to be the right answer. At the count of 3. 1, 2, and 3. Keep it there. You know, I thought it was a really good lecture. And you did too, because you didn't ask me any questions. Except finally, after waiting a long time, I got one question about, a good question about the middle atom there. In spite of my great lecture, less than 30% of you got the right answer the first time around. So, you know, in a sense, you've helped me make a really important point. Because by the way you're voting, you have been telling me, Eric, your lecturing sucks. Which is actually the point I wanted to make, right? I mostly transferred information. You've had some time to think about it in this one question, but it's by far not enough to really finish the deal. The good news is that more of you got the right answer the second time, even though it was very, very low initially. It was, you know, there was maybe a few correct answers, and I know you want to know what the right answer is, I'll tell you. And now it was, maybe around 1/3, which is still not very high. The correct, and oh, by the way, online, they're doing quite well. Can you project that?
No, but we.
Okay, well, we're not gonna project that. So the right answer is, look at that. There is not one person typing or looking at a smartphone. Everybody's looking at me. It's just a hole in the The right answer is number, oh, my clicker is not working. 1. Okay, listen, I'm sure that by now you can't have forgotten. It's okay, it's okay, it's okay, it's not a test. I love it. Hello? It's okay, it's not gonna affect your salary or your promotion chances or your graduation chances. Don't worry, there's no record of how you voted. Now, I don't want you to be in bed tonight at 2 a.m. wide awake, still thinking about this question and why it is that the whole increases. So let me take a few minutes of my precious time here to explain to you why it increases. Imagine you have a jar of marmalade in the refrigerator, right? It's a glass jar with a metal lid. It's in the refrigerator, it's cold. You're going to have breakfast, you want some toast and put marmalade on it. You take the marmalade out of the refrigerator, you can't open the marmalade. What do?
Knock.
Yeah, you might be able to hit it too, but there's another way. You run the cap under hot water. And the lid expands, right? The lid, which consists of a ring and a plate. The ring expands and it's easier to open. You say, well, you asked about the rectangular plate, not about the marmalade lid. Well, let's see, can I find a piece of paper somewhere here? Imagine you have a metal plate. Here's my metal plate. No hole in it. There's no hole. I take a marker and I draw a circle. So now I have a plate with a circle. Can you imagine that? Okay, I put the plate with the circle in the oven. I turn the temperature up. The plate expands. What happens to the circle? It gets larger, right? The plate gets larger, everything on it will get larger. The circle will get larger too. You think that's unfair, there's no hole. If there had been a hole, then the metal will expand into the hole. Let me show you what's wrong with that reasoning. Imagine that we all go outside now, in the courtyard of this building or in front. We all go outside, and we all hold hands, forming a large circle. We are the atoms at the edge of the hole. I'm going to close this poll here. Online, they did good. At the end, 63% got the right answer. I don't know how they managed to communicate with each other. So can you imagine that? Each dot is one of us, right? We hold hands like this. And at the count of 3, I ask everybody to step in towards the center of the hole. What happened to the distance between us? It's smaller. It can't get smaller. You're shaking more, I'm shaking more, everybody's shaking more. We need more space. This would mean less space. So let's go back here. How can we make more space? Well, we could remove a few of us. But the problem in solids is that atoms hold each other in place and they cannot disappear or they cannot move in a different direction from their neighbor. The only way to make more space is to make the hole larger. Okay, back to peer instruction. So the very first year that I did this, I showed a doubling of the learning gains, not a 20% increase, 10% increase, no, a 100% increase. And over the years, so that was the learning gain when I lectured, and this was the learning gain with speed instruction after a few years. The first year doubled, and then by asking better questions in class, I managed to even triple it. That's a huge effect, okay? That's an enormous effect. And other studies have shown that there's better retention, because once you have this aha moment, you figured it out. You know it not just to pass the exam, you know it for life. And even if you forget the fact, you learn to trust your thinking skills rather than your memorization skills. So I hope, this brings me to the end of where I want to be. I hope that I convince you that education is not just about transferring information. It's not about getting our students to do what we do, or our students to know what we know. I want my students to stand on my shoulders and to be able to solve problems that I cannot solve. Society is facing a lot of problems: climate, energy, health, privacy, all kinds of conflicts that are going on. Problems that this generation now doesn't know how to solve. So we need to equip the next generation with the skills to be able to solve that. And I think the only way to teach that is to teach them the thinking skills rather than simply transferring information or transferring knowledge. Thank you so much for your attention.